So today we're going to start covering hydrostatic forces. And we're going to define what they are on horizontal surfaces, and then we'll go through a problem on a rectangular wall. Let's just do a little review. Give me one form of the pressure equation. Force over area, yep. So if we look at that, pressure times area gives you a force, right? So if you can find the pressure on something, you multiply it by the area, boom, you automatically what they call the pressure force. Okay, what's the other pressure equation if it's a function of depth? Plus, perfect. Yep. The pressure at the top plus rho GH. Everything you had to do in exam 1, you're going to be using in this. Okay? So those are two very important equations that you're going to use here in a second. Okay. Let's draw two shapes. It's not perfect to scale, but and we got water in the bottom section. And there's some sort of oil in the top section. Now the scaling might be off, but what I'm telling you is for each different shape, one's like a cylinder, one's like a pyramid, the amount of oil, which is the brown up top, is 2.4 millimeters. And halfway down to the bottom is water, which is 1.5 millimeters. Okay. The bottom area is the same too. 3 millimeters. So the radius, again, the scaling might be off. We have two different shapes with the same dimensions, kind of. I want to figure out what the force is at the very bottom of those shapes, that what I colored in purple. Okay. If it's a circle on the bottom, how do you find that area? Pi r squared or pi d squared over 4. Okay, so that's the area. If we multiply by pressure, then we'll figure out what the force is, right? So what's the pressure? Rho GH plus some top pressure, right? Okay. Is H the same for both? Yeah. So the force is going to be the same for both because it's the same depth, same amount of liquid up top and bottom, and the area is the same. Well, if they're both, say they're both open at the top of the atmosphere, then you would get the exact same amount of force at the bottom. Okay? Because we know pressure is a function of depth only. Okay? So if we want to figure out what this pressure is, well, say they're both open to the atmosphere up top. So sometimes you'll see this triangle. So it's P atmosphere plus rho of the oil times G times H. And we'll call these H1 and these H2. Plus rho of H2O times G times H2. And I'm going to do a few things. I'm going to just say gauge pressure. Right? So what happens to the atmosphere on the right side of that equation? It goes away because it's zero. Okay? How can we rewrite density of oil in terms of specific gravity of oil? Yep. And I just changed my symbol for water to W. Is that okay? We could do one more thing just to kind of make it easier. What is density times gravity? Specific weight. Yeah. So you'll see a whole bunch of combinations of things. And that's why I had to teach you all that before, right? You see how everything now we've learned in the previous 5 weeks, we can then apply now to make life easier in our equations? And I don't know, let's just plug some numbers so you have it. Specific gravity of oil is 0.9 times 1,000 kilograms per meter cubed times 9.81 meters per second squared times 2.4 meters plus, let me zoom in a little bit more, 1,000 kilograms per meter cubed times 9.81 meters per second squared times 1.5 meters. So if you want to remember what the specific weight of water is, it's just those two terms, right? So 9810 Newton over meter cubed. Looks like a squared though, it's a meter cubed. Remember you saw that unit in the falling ball viscometer, given specific weight? And this pressure we got to be 35.9 kilopascals. And now we can find the force. And I'm okay now, if you want to just write, so a little, or that we did find that, P times A. Because you've written enough, you kind of now know that pressure is force over area. Well, now you can say, well, F is P times A. And the force equals P times pi d squared over 4. So F equals 35.9 kilopascals times 1,000 pascals over 1 kilopascal times pi times 3 meters squared over 4. Rectangular walls. Nope. Ah, where'd that go? Okay. Oh, let's see if I can line this up perfect. Pretty close. I'll have to move it up just a tad. So we have a dam that's projected in and out of the screen. And we have a free surface. And we have the ground at the very bottom, which is that brown line. All right, what we need to label next is this height, H. Oh, and let's label light purple. Right about there, actually, probably more there. And a little down farther, right there. So that light purple is the centroid of from where the water, the half of that water height. Okay. And what's the next line I want to draw? Let's wait. Draw this. As you can see now how important sketches are going to become, right? Straight edges. You want to label variables. You want to try to avoid numbers because it's going to be really cluttered. Okay. Now, can someone tell me what the pressure distribution is going to look like? The top of that down. Okay. Some sort of angle. It's a linear line, all right? Okay. So let's make it linear. And I will do green. Look at that. Fancy pants. And I can do these arrows green. Oh. So that green shape I just drew, you don't have to do on your sketches, but I wanted to put this in the notes. That's the pressure distribution, right? Can someone tell me the top pressure? It's atmospheric. Do you want to use 101 or do you want to use something easier? 0. Okay, you want to do gauge pressure. Okay. Other thing is, so on the left side, if there was no water, okay, it would be, say there was just this piece of jam, I don't know, this is this right here, okay? Say your side, whatever, it doesn't matter. There was no water on this side or no water on this side. What's acting around this? Atmospheric pressure on this side, and it's also acting on this side. You see, atmospheric pressure acts this way to this way, but then it acts the other way. What happens to those? They cancel. Over here, now we add water. You still have atmospheric pressure on this side, right? Because you have to include it in this pressure term. But what about the right side? What's acting on this side? Atmospheric pressure too. So they cancel. So you don't have to worry about. That's again why we kind of go with 0 anyways, because it makes life easier. So you never have to worry about adding atmosphere on here because they cancel because they're on both sides. Does that make sense? Okay. So say I drew a distribution. Did I draw this green really right if I wanted to include atmosphere? I should have started a little bit over to the left, right? And then, but that's fine, okay? So just remember, you don't have to worry about atmosphere because it acts on both sides of this dam. We only have to worry now about the rho GH. All right, good. Questions on this? So you don't have to, I'm going to erase this right now, these green, okay, because it's just so much, too much right now for the sketch. Come on. And you don't have to label that. And, oh, I did too much. There. So right now, you're missing two other things on a sketch. The most important one is going to be this one. This is your resultant force from the pressure. So F. I'm going to call it FR, subscript R, okay? Why is it below the centroid? Ah, yes, because we know that force is a function of pressure, and the pressure distribution I just erased is heavier at the bottom. So that force actually acts below it because it's like a weighted average. Okay. On this case it is, but don't always assume. If it's not a rectangular shape, which we'll talk about in a few classes, it's not 2/3. But yes, it is because because of this rectangular wall. Yep. This acts, and let's draw this in gray. No, you won't see that. Be probably green. And I will do this. This is what, with the distance down, we call HP. This is kind of the center of pressure. That's what they call it, okay? So on your sketches, this is what I want to see. I want to see it every time you do a problem. Okay? So I want you to practice labeling and organizing and understanding this type of value. Okay?
What does HP stand for?
It's the center of pressure. So this force, FR, is what they call, it acts at the center of pressure. Okay? So always remember that your HC is half of your water depth. The hydrostatic force, due to the water pressure, acts below the centroid at the center of pressure, which we label HP. Now, over here on the left, you have FR, that's P average times A. Okay, where P average is rho GHC. And then just for reference, for this case, 2/3 times H. But if you notice, this 2/3 is only true under this heading, rectangular walls. So let's have some numbers in your problem here. We'll use that same sketch. So here's an example. So given H, 10 meters. The width, 10 meters. We want to find FR and HP. In sketch, I'm not going to redo it, but just see above. Solution.
Actually, we can write some assumptions down.
First one is it's static, meaning that the water is not moving. Okay. We're going to start looking at energy later in the semester where the water starts moving and relating velocity and pressure. Okay. But not yet. So it's static. You say H2O is incompressible. We talk about that in this class? Incompressible, what that is? I think we did, right? Sort of. Just means that the density stays the same all the time. Okay. And that'll be it for now. Okay, so under solution, let's have a heading. And let's just type it hydrostatic force. Or you can say find FR, it's up to you. So FR equals P average times A. And you could do this. I'll just plug in P average, which is rho GHC times A. Now, do I have to do that? I could have just said find P average, found that number, and multiply by area. It's up to you how you want to do this. But as long as you have a heading and you give me some equations. Okay, so let's sub. Density is 1,000 kilograms per meter cubed. And actually, we forgot that in our givens, right? So you can go back there. And include it. Times 9.81 meters per second squared. Times HC, which is 10 meters over 2, times the area, which is 10 meters times 10 meters. So the area is what the water is touching. You see that? It's 10 meters high, but in and out of this screen or page is 10 meters width. Okay? So that's where the area comes into play. So you get 4905 kilonewtons. That's huge, right? I mean, that's a lot of water. Questions? All right. Can I go right there? Is that okay? Yes?
You want us to write the sub as a heading?
You don't have to. It's fine. Okay, now find HP. HP is just 2/3 times H.